Greetings! Welcome to supplementary video for discussion question 10 part 2. Okay, so back in part 1 we got pretty familiar with our newfound friend here. P of t is equal to p sub 0 e to the rt, sometimes affectionately referred to as the PERT model. Well, one thing to notice about this is an exponential function. Just like back in our previous work not that long ago, in fact in this module, we looked at y was equal to, say, a function of x, say b raised to the x power. And we knew that that function had an inverse function. In particular, it had the logarithm as its inverse. And so we know that the exponent on a base b that got us y was equal to x. Okay, so we know that's the relationship between an exponential function and a logarithm. Well, the same thing can be said about base e. It's just base e is one of our special logarithms. So let's remind ourselves real quick that one of our special logarithms is base 10. So log of x is the same thing as log base 10 of x. And this is referred to in the business very often as the common log. And it's really an artifact of the fact that we have 10 fingers, okay? That we work in base 10 system. But Mother Nature, she doesn't work in that. She works in different bases. In particular, she works in logarithm naturel, or ln, for the natural logarithm. And logarithm naturel of x is defined to be logarithm base e of x. Okay, so if we go over and take a look at our calculator real quick, let's get to the calculator here. There it is. You'll see that we have the log key, which we've used previously, but we also have ln, which is our base e key. And in the previous video, we noticed that the second function above it was e to the x. Kind of a cool little cheat sheet built in. We know that this is logarithm base e because the second function is e to the x. We know this is logarithm base 10 because the second function to it is 10 to the x. Okay, so let's take a look at a simple example here. So let's say you had 25 was equal to 5 times e to the 0.3 t, and we want to solve for t. So if we were to do that, first thing we're going to need to do is get rid of this leading coefficient. That can't be there. It's going to be in our way. So we'll divide both sides through by 5. So we'll take 25 divided by 5 is equal to e to the 0.3t. Okay, well 25 divided by 5 is 5, so that's 5 is equal to e to the 0.3t. All right, now in order to get this out of being an exponential equation and being into a logarithmic equation, we need to remember the following relation here. And I'll go ahead and put this in, what do we say, we'll put it in red. That if I gave you y was equal to e to the x, then what that tells me is that the logarithm natural of y will be equal to x. In other words, we know that that's the base e. So if I come back over here, let's switch back into black, and I say ln of 5, that's going to be equal to whatever my exponent was on my e. So ln of 5 is equal to 0.3t. Okay, now divide out both sides by 0.3. And we end up with ln, let's do that a little cleaner here, Mike. That's ln of 5 divided by 0.3 is equal to t. So how about we get a decimal approximation of that on our calculator? So let's go ahead and grab that real quick. Let's grab our calculator. And so to do a decimal approximation of that, I'm going to come in here, clean out my home screen, and let's say ln of 5, close off my parentheses, divided by 0.3, and voila. That is the exponent I need to raise an e to, times 0.3, of course, and then multiply that times 5, and I'll get back 25. All right, I'll let you verify that on your own. Okay, now as it turns out in the real world, this model is used very commonly for exponential decay models like radioactive isotopes. And many times what we're given is we're not given the actual exponential decay rate. What we're given is the half-life of the isotope. And so what we'll be asked to do many times is find a model that corresponds to the half-life to the radioactive decay of that isotope based strictly upon what the half-life is. Okay, so this will be the only thing they give us. So let's see if we can do that. Let's take an example of a particular not an asytope, an isotope, particular isotope that's rather a nasty one that showed up after the 40s once we started doing above surface nuclear testing, which was not a really good thing. I'll let you read up some more about that if you haven't already. So 90SR is strontium 90, okay? And so strontium 90 has a half-life of 28.8 years, which means that in 28.8 years, whatever you started off with, you'll have half of that radioactive isotope left. So looking at our model, P of t is equal to P sub 0 e to the RT, we would like to come up with the specific model. In particular, what we're going to really need to know is what is R, what is our radioactive isotopes decay rate, so that we can come up with a model for any particular given amount of strontium 90. We can tell you how much will be left after T years. So if we know that the half-life is equal to 28.8 years, what that means mathematically, what this tells us right here, is that P of 28.8 is equal to 1/2 P sub 0. In other words, after 28.8 years, we'll have half of whatever the initial amount was that we started with. So let's go back and let's take that information. Let's plug all of that into our model here. So that says that P of 28.8 is equal to P sub 0 e to the R times 28.8, okay? But wait, we know that this right here, the P of 28.8 is 1/2 P sub 0. So let's go ahead and substitute that in over here. In other words, let's put in 1/2 P sub 0 for that. And we know that that's going to be equal to P sub 0 e to the R times 28.8, okay? All right, so notice that what I can do is divide out, just as we did in our previous example, divide out what our initial quantity was, our P sub 0. And we end up with 1/2 is equal to E times R, or raised to the R times 28.8. Aha! So now all we need to do is bring out our newfound friend, the natural logarithm. So the natural logarithm of 1/2 is going to be equal to 28.8 times R. And so then we'll divide out both sides of this by 28.8. And what we will have now is what our newfound friend for strontium 90 is. Its decay rate, its exponential decay rate. So ln of 1/2 divided by 28.8 is going to be equal to R. So let's get the calculator in here now to help us out with that. So clear out all the crazy numbers we got in here, and let's go ln of 1 divided by 2. You can put in a 0.5 if you'd like, and then divide that by 28.8. And we see that the exponential decay rate, which our R is negative, indicating a decay model, is negative 0.024067. We're going to go probably out to 6.8 and round off there. These models are very sensitive to this exponent. So, really in calculation, you should carry it out to all the places of accuracy that your calculator's got. But we'll just write down for our model. We'll go out, say 1, 2, 3, 4. We'll go 5 places. That'll be a good place. Okay. All right. So let's go ahead and clean up my board here. So cleaning up our board and getting the new model back, what we were asked for is we want to know what is P of t equal to P sub 0 e to the RT going to be for strontium 90, or for 90SR. Well, really all you need to know is that number right there, which we now have. We've got it right here in the palm of our hand. So let's slide this off to the side so I can still see it. And so we've got that. Whoa, that's an interesting thing there. Let's get rid of that. start over here again. So what we've got is P of t is equal to P sub 0 e to the negative 0.0, let's see, what was our number again? 0.2407. If we round off correctly, times t. Don't forget your variable. That's really important. In other words, this is still a function that has to have a variable involved in it. Okay, so that will be the model that given any initial quantity and any time, we can tell you how much strontium 90 is going to be left after that many years. Okay, let's go ahead and leave it at that. Of course, do not be shy about posting questions to the discussion board for question and answers, the Q&A form, or you can send me questions directly and I'll probably respond to you back there.